Random error has a variation that is not predictable and cannot be adjusted or corrected. The variation that occurs in between the two farthest points of the distributed values is what determines the range. The unpredictability is what makes random error different from systematic error. Systematic error had some expected trends that could be corrected where random error does not. When there is no systematic error that lies in the uncertainty is only from random error and a complete reflection of how precise a measurement is. The source of random error may or may not be known. However, sources that may cause random error include the following: equipment that is not sensitive enough to pick up slight or fine changes, noise or extraneous disturbances that are unpredictable or random and cannot be completely accounted for, imprecise definition where the exact and defined dimensions cannot be quantified. Precision and random error are both describing the margin of uncertainty. One way to look at this is random error is inside the margin of error, where precision is on the outside of the margin of error, encroaching in on the very edges of random error. As you can see in this slide, the farther out the distribution is from one measurement to another, the less precise the measurement becomes. Conversely, as the distribution of random error is drawn in closer together, the precision increases and the random error decreases. This clearly reveals there is an inverse relationship between random error and precision. This relationship between random error and precision does not depend on how close or how far values are from the true value or standard, solely operating as a function between the distribution of values. Looking at the slide we went over describing the conventional syntax and notation of a reported measurement, there are arrows indicating that there is a direct relationship between the number of digits reported in a measurement and the level of precision the measurement has. When the number of digits reported in the measurement increase, the precision increases as a direct relationship. Let's see how this works. Looking at these two numbers, 137.12345 and 137.12345, the value 137.12345 is more precise than the value 137.12345 because there are more numbers or digits in the number 137.12345. Okay, so we know this because I told you, but why is this so? Why does the precision increase when more numbers are in a measurement? Let's look at this ruler, with the arbitrary numbers 1, 2, and 3. We know that we report a number to one digit past what is certain as an estimation. The ruler has one digit, so we could estimate out to the tenths place 1.0. Then we know by convention the last estimated digit is where the uncertainty lies, and the reported number really means there is a range of plus or minus 1 unit of the last digit. The last digit is to the 10th place where the estimation and uncertainty lies, so 1.0 could be 1.1, it could be 1.0, or it could be 0.9. Anywhere within this range would be acceptable to report given the precision of this instrument. The key point is there is a range in the tenths place plus or minus 0.1. Let's zoom in. This is the area we need to stay in at a measurement reported to the precision of 0.1. If we have a ruler that is more precise where the certainty is to the tenths place and the estimation is to the 100ths place, we can report a value to the 100ths place. So, 1.00 would mean 1.00 plus or minus 1 unit of the last digit. This is saying we are certain up to the 10th place, and the 100ths place is where the estimation and uncertainty lies. The range of uncertainty now becomes 1.01, 1.00, and 0.99, tremendously closing the gap of uncertainty. Let's zoom in another increment. If our measuring device is more precise, adding one more increment unit, we now have certainty to the 100ths place, and we can report the number to the 1000ths place where the last digit is an estimated guess. We know by convention, the last number has a deviated range of uncertainty of plus or minus 1 unit, so 1.000 really means 1.000 plus or minus 0.001, closing the range of acceptable error even farther. The acceptable reportable range is now 1.001, 1.000, or 0.999. You can see as we increase the decimal from tens to hundreds to thousands, the range of uncertainty decreases, the certainty increases, and the precision increases. Let's recap and clarify. At an uncertainty level of 0.1, we have a range shown in black. At an uncertainty level of 0.01, we have a range shown in blue, decreasing the uncertainty, increasing the certainty, and increasing the precision. At an uncertainty level of 0.001, we have a range shown in purple, decreasing the uncertainty even more, increasing the certainty even more, and increasing the precision even more. As you can see, the more digits we have, the less uncertainty we have in the measurement. The more certain we are about a measurement, the measurement becomes more precise, thus more numbers, more precision. So now, we know a tremendous amount of information about a measurement at a glance. Let's look at the number 859.257. We know right off the measurement is certain up to the hundredths place. We know the last digit 7 is an estimation. We know the last number 7 is where the uncertainty lies, of plus or minus of 0.001. The measurement has 6 reported digits, so this measurement would be more precise than a measurement with only 5 reported digits and less precise than a measurement with 7 reported digits. Okay, so we can tell how precise a measurement is when we compare it to another measurement, but how can we tell how precise a measurement is when there isn't another measurement to compare it to? We can do this using percent uncertainty. Okay, so what is percent uncertainty? Percent uncertainty. Percent uncertainty is a relative idea that is bound to the measurement itself. If a person said something is big, well, okay, how big is big? Big compared to what? Is this blue circle big or small? Comparing one thing to another can clarify things tremendously. Okay, now answer the question. The answer becomes obvious once the question is put into perspective. Perspective can make a big difference. The amount of uncertainty becomes much clearer once we compare the uncertainty to the total measured value. Percent literally translates to divided by 100, so percent of anything means it is divided into 100 equal parts, and we are comparing an amount to those 100 parts, so when we say percent uncertainty, we are saying the total is evenly divided up into 100 total parts, a portion of that total is uncertain, and we are comparing this portion to the total portion. If we would say we have 10% uncertainty, we are saying we have 10 parts, and we are comparing it to the total which was divided into 100 parts for perspective. We could say the measurement has a 1 out of 10 ratio of uncertainty. For a closer look at the difference between fractions and ratios, look at the mathematical appendix videos titled Fractions versus Ratios. Percent uncertainty gives a good way to judge the relative worth of a measurement without comparing it to other measurements. A good example is when a graduated cylinder has a place saying it is good to plus or minus 3% of full volume, or plus or minus 1% of the reading, or good to 1 part in a million. To calculate percent uncertainty, we have the following equation. Delta Z divided by Z times 100 equals percent uncertainty. Uncertainty is denoted delta Z, and the total measured value denoted Z. So, if the uncertainty of a measurement 2.4 is plus or minus 0.1, then we follow the equation. Delta Z divided by Z times 100 equals percent uncertainty. So plugging in the numbers, we have 0.1 divided by 2.4 times 100, arriving at 4.1%. If a measurement is 3.40 with an uncertainty of 0.01, then the percent uncertainty is 0.01 divided by 3.40 times 100, arriving at 0.29%. A measurement of 2 plus or minus 1 has a percentage uncertainty of 50%. You can tell right off very far away from what would be perfect, and the amount of uncertainty is enormous. This pops out well when we see it visually. To show you in black, this is what we are uncertain of. In contrast, a measurement of 1.00 plus or minus 0.01 has a percentage uncertainty of 1%. At a glance, we know this is not far from what would be considered perfect. To show you a visual difference, look how much smaller the uncertain black is in comparison to what is certain in red. This is what is represented in the fraction part of the percent uncertainty equation, where delta Z is the uncertainty and Z is the total amount. The bigger the difference between delta Z and Z is, the smaller the percent uncertainty gets, as you can see here visually. We can do this by decreasing delta Z or increasing Z. A percent uncertainty of 1% closes the range of error tremendously, making the measurement much more precise and useful. Stopped here getting froggy. We can see there is a clear relationship between uncertainty, the numerator portion of the percent uncertainty equation delta Z, and percent uncertainty. As delta Z decreased, the percent uncertainty decreased, and vice versa. It should also be apparent that as the decimal place goes out from tenths to hundredths to thousandths, the uncertainty decreases, thus delta Z decreases. Okay, so to this point, we have only illustrated how the phrase, more numbers, more precision, works with the numerator portion of the percent uncertainty equation. We could see that as we added more numbers to the right, the range of uncertainty narrowed tremendously. That doesn't completely answer the question though. What if we add numbers before the decimal or to the left? Does the phrase, more numbers, more precision, still apply? Let's look at the denominator, our total measurement portion of the percent uncertainty equation. The general nature of a fraction is that when the number in the denominator gets bigger, the answer gets smaller, so the same thing happens in the denominator of the percent uncertainty equation. The denominator of the percent uncertainty represents the total measured value, z, so the more digits z has, the less the percent uncertainty is, and the more precision the measurement is, thus more numbers, more precision. Let's look at the percent uncertainty equation and see how this works. The two numbers 234.5678 and 1234.5678 differ only by an added number before the decimal. Using the number 234.5678, we plug the number into the equation as 0.0001 divided by 234.5678 times 100, arriving at 4.2631 times 10 to the power of minus 5. Using the number 1234.5678, we plug in the number 0.0001 divided by 1234.5678 times 100, arriving at 8.1000 times 10 to the power of minus 6. This shows that a number with more digits arrives at a smaller percent uncertainty value. Drawing from our analogy, the smaller percent uncertainty means we are closer to perfection, and the phrase more numbers, more precision hold to be true. When the differences between the black uncertainty and red certainty is bigger, the less percent uncertainty there is, and the closer we are to perfection. We can increase this difference from either making the uncertainty smaller, giving a direct relationship to percent uncertainty, or from making the total measurement number in the denominator bigger, giving an inverse relationship to the percent uncertainty. Summarization. The uncertainty in random error lies in how close one measurement is from another, so random error is related to precision. The variation that occurs in between the two farthest points of the distributed values is what determines the range of random error. Random error has a variation that is not predictable and cannot be adjusted or corrected. Random error is unpredictable. Random error has an inverse relationship with precision. Random error decreases, precision increases. Random error may be known or unknown. Random error can be caused by the lack of sensitive equipment, noise, or extraneous disturbances, an imprecise definition. Percent uncertainty can describe how precise a measurement is. The percent uncertainty equation is delta z divided by z times 100 equals percent uncertainty, where delta z is uncertainty and z is the measurement or total. Delta z has a direct relationship with percent uncertainty. Z has an inverse relationship with percent uncertainty. When there is no systematic error in the uncertainty is only from random error and a complete reflection of how precise a measurement is. More numbers, more precision, less uncertainty.